Question 3. Right, yeah, I guess we can talk about, or I guess we can read the problem again. I think most of this is actually like not at all related to the actual problem. But yeah, Merry Christmas. Um, Hack it, reverse the secondary encryption, you get the primary encryption keys. I don't understand what this means. And then the white whale, what does the white whale have to do with this? I feel like these are both red herrings. I ever try like white whale as passcodes, the GPG, and yeah, I didn't expect that to work out. Right, so we get p3.zip. P3.zip inflates, or when you extract the files inside, you get ciphertext, discarded values, encoded values.gpg, plain text.txt.gpg. We won't be able to get into any GPG files. Sandtypecrypt.py, which is really nice. It tells you how it's done. And these are files I created, and usevalues.txt. So my initial idea was to do really bad stuff, or very unproductive stuff, where I would grab like the first letter, assuming that it was a C, assuming that in plain text it's a C, because we can XOR, and XOR is a reversible thing. So if you have A XOR B, then A XOR A XOR B just is going to give you B. If you do Broussard's class, this will become a lot clearer, but it's just the way that XOR tables work. A and B are just like any number or any number that you want to apply. It's not like the letters A and B specifically. But yeah, so I was trying to do really weird stuff, but you're not supposed to do any of it. As I needed to be, I guess, walk through most of this. It was no Python random function. Yeah, there we go. I needed to walk through a lot of this because I was really bad. And so the first thing that you have to see is Python uses the Mersenne Twister as its core generator that produces blah 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 a period of 2 to the 19937 minus 1. This is important because it means that the Mersenne Twister it has this period, which means that oh yeah, this is a big warning that you're supposed to attack. And then the Mersenne Twister is basically what we need to attack here. I found the Mersenne Twister to be super cool, or at least it's interesting from like a stats perspective. Let's just grab implementation. Oh wait, let's just go to Wikipedia first, so that we can know what the exploit is at all. The exploit is this. It's not cryptographically secure, which means that, or it's because of this, that observing a sufficient number of iterations, 624 in the case of MT1937, allows one to predict all future iterations. This is basically the exploit. I found it interesting, or okay, let's find the exploit and all that kind of stuff. So we found our friend James 727's implementation of the Mersenne twist. Thank you very much, Mr. James 727. Let's go back. Where is it? BitTorrent in Python. That's actually pretty cool. Dynamic programming workshops. Oh my god. DP time. Where did it go? Nah, there were MPP. Okay. Let's go to mersennetwister.py. Okay, so you have a bunch of initial states or initial values. Here's what we care about. That to get a random number, they do this, right? Now, what is the smarter way of doing this problem? Is to realize that, oh, Iliad is always correct, right? And that there's always going to be some guy who's written a random module cracker, right? And not only have they written a random module cracker, they've made it available as a library, right? You should always think, what would somebody who is smarter than me do, right? I, however, decided to go the route of the complete dumb person, let's just say, and implement the crack myself. I would not recommend this. This takes too much time, isn't worth it. Unless it's for an educational purpose, right? So let's just do that. Let's just implement it ourselves. Now, we have this, right? my first question that I want to answer at the end of the stream or at some point in the stream is, why do we need to do this 32 times? That's my question. Actually, this will make sense over here. Let's just first explain it first. No, did I seriously? Okay, whatever. We have this, right? We have an XOR and it's bit shifted to the right by L. What is L? 18, right? So we make a method that says undo a right XOR. That's right bit shift and an XOR. That means that for each value in the first 624 values, you first have a value X, right? Then we undo that shift, which is effectively, let's just do this here. So if we have, it's 32 bits, right? So 0, actually no, let's not do 0, let's do like, okay, there shouldn't be any 2's in here, it's just binary. Well, no. Okay, man, that's 32. Okay, if we were to bit shift this 18 to the right, we get 1, 2, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. When you XOR these two, if you XOR something with 0, it doesn't change, right? 0 XOR 0 is 0, 1 XOR 0 is 1. Your first 18 guys are going to stay the same, right? Now the question is, what happens at the end? 1 XOR 1 is 0. 0 XOR 0 is 0. This is 0, 0, 0, 0, 0. 0 XOR 1 is 1. 1, I don't know, keep that 1, 1. That's a 0. And then you get the idea, right? You just keep doing that, right? Everything else after this, like the, what? 32 minus 18, what is that? Like 14? Yeah, so you have 14 numbers here, 14 bits that get counted, and everything else just tossed out. How do we undo this? It's very much just, if you look at this, right? You bit shift this, you get this. Or if you bit shift this and XOR with this, you get the original, which is exactly what we're doing here, right? You take that value, you XOR it with the value and like shift it by whatever amount. I think so. Or am I doing this completely incorrectly? I explained this wrong. My fate also. It is safe. Oh shoot! Oh my god! It is safe. I didn't know. I'm dumb. My favorite problem. This is possibly my. I mean, it was a fun problem. I personally like the next problem better, just because this problem just feels like, oh, I don't understand why you're supposed to do this 32 times. I'll explain the 32 part, right? And apparently you're supposed to do this process of like of shifting and then XORing it 32 times, right? I don't get it. Why 32? This is my question. And the question that I want to answer by the end of this, I'm not sure if it's something with statistics. I'm not sure if it's like a central limit theorem kind of thing or something like that. If anyone would like to explain in the chat, that would be awesome. But if not, I guess we can figure it out together. And then I'll bust out one note and we can do some mathematics or something. I don't know. Anyway, you do that. Same thing with the stuff where you apply the mask and technically destroy data, but we're bit shifting it first. So the destroyed data isn't actually important. Okay, yeah, for B and C, there's the stuff 0x that, 0x that. That's here, right? You do that. You append each value to the state, right? So in your random number generator will have some state, right? So I think the way that I did it originally was right. So imagine if we have something here, right? We do print r.getState. You do this first. This is going to be something different. And the way that I did this was I created a test number, and then I use that to crack like a test random number generator or pseudo random number generator. So let's do this first, and then we can talk about. Right, we don't need any of this either for just this. Right. Okay, let's do it. Oh no, I need to get out of this and go to P3. All right, Python. T tab because I'm lazy. Desktop 5. Oh my god. yes. Python 3. Okay. Yeah. So we have this huge state, just a bunch of numbers that decide how, oh my god, that decide how new random number generators should be made. If you want, do you want to see a test state compared to like a test state and then cracking the test state, or do you just want to see the final exploit? Oh my god, which one do you want to see? I can do both. It's just, what do you guys want? Come on. It does kind of suck that you can't really see anybody typing in the chat, but I mean, whatever. Chat. There are chat settings. Oh my god. What is a followers only chat? What does that mean? Oh, bro, what? I don't care. Nobody can chat. I don't really care about that. One icons. Wait, that would be interesting if you like force whichever one is faster. Okay, I think it's the final one where you just show the final one. So I read discard from the discarded values. You apply the algorithm. Let's delete this. You make a sample state, right? Have a key stream. We delete this. We set the state as the one that we create. So you go for 1424 because we need to fill up that many words. We have, what is it? We process 624. Oh, wait, why is it 1424? I don't remember anymore. There's a very specific reason now. What was the reason? I think it processed the first 624 numbers. Right. Was it like the length of discard? It was like 1724 or something? How long is the ciphertext? And how long is discard? I think that's what it is. It's something like that. 1 3 test apply 1000. Right, yeah, we have it. Okay, don't worry about this. Don't worry about that for now. Why did I do? Oh, right. It was 1024, and I wanted to get rid of the first 400 numbers. Right, yeah, 1024 plus 400. You're the first 400. You just toss them. You add the next ones, and then you just XOR it together, and then you have your plain text, which is this. Call me Ishmael. That's from Moby Dick. And then we just look at it and we find that our flag is here. The flag is CTF. Don't use insecure PRNGs for crypto. Control C. Slap that in. Submit. Okay. Cool. What was the hit for this? Oh yeah. Okay. So just say that don't worry about GPG. What is the passphrase? I mean, I guess that would help if you knew the passphrase for all of them.